This is the very first geometry lesson. It talks about some of the things that we don't really define. First thing we're going to talk about is a point. A point. What's a point? Well, some people say it's a location in space. Some people say it's a dot on the paper. I say it's right there at the end of my finger. See right there at the end of my finger? See it? See the point? Do you see the point? No, you don't, because you can't see it. You know why? Because this location in space that I'm choosing right here, that's right at the end of my, or how about this one right here? This point right here, right between my fingers, right there, it's a location. It's something that I could make some coordinates for and define. But basically, it's just something that's in my head. It doesn't really exist. It has no length, it has no width, it has no depth. And I live in the three-dimensional world, and I'm pretty sure you do too. So really, the only things I can deal with have 3 dimensions. And this one has zippo, no dimensions. So I can't see it. I can't grab it and throw it at my friend. I can't grab it and make a pile of them and do things with it. I can't do anything with it. It's just this location, you might call it, or it's this right here at the end of my finger. That's just in my mind, thinking about it. Okay, well, let's think some more about it on things that we could do. So say, for example, I take this as a point in space, the end of this pen. This pen right here, this is a pen that I got when I was in the Marching Owl Band of Rice University. Rice Owl Band. Go Owls. Cool. Okay, so I'm going to take that as a point in space, and that'll be a little bit easier to refer to. Okay, if I take this point, and then if I take another point. So I'll take this point right here. Okay, the point at the top, a point at the top of this thing. This is a Dr. Pepper bottle that commemorates something from the Houston Cougars. 1976, they win the Southwest Conference. Okay, so they made this bottle, Dr. Pepper did. Because I've got a point right here at the top of my Rice Owl Band pen, and I've got a top point up here, I'll pick that one right there, up at the top of my Dr. Pepper. And let's say between this point and this point, I'm going to put another point. I'll put one right here. You know, I still can see the top here, but I can't see the point, the geometric figure, the point. And I can see the top here, but I know it's right there, and I know that's telling me where it is and helping to remind me where it is, but I can't actually see it. And this point out here in the middle, I sure can't see that. But let's say they line up. They're in a line. And then what, instead of just that one point, what if I put a million points between the top of the Rice Owl Band and the top of the Houston Cougar? A million. Okay, now remember, points have no length, no width, no depth. If I pile a million of them in here in a nice straight line, can you see a million of them? I don't think so. Even if it's a million no widths and a million no lengths and a million no depths, it's still nothing. It's not there, you can't see it. Okay. Right now I've got 1,000,002 points that are no width, no length, no depth that I can't see, but I know they're there because they're there in my mind. What if I go ahead and extend in a straight line, and I go on and up here like there, and I go on down here like that, and I do it kind of like this, okay, something like that, and I put another million here and another million there. So now I've got 3,000,002 points. Can I see them now? Oh, no, I can't see them now. A million nothings. 3,000,002 nothings is still nothing. So I still can't see it. But then something really interesting happens. What if, generally along the course of this yellow stick here, I put an infinite number of points? An infinite number. Remember, infinity is not a number. It's not like a really big number. It's like forever. It's It's one of those kind of things that aren't clearly defined. So I've done that. Guess what happens when I put an infinite number, not merely 3,000,002, but an infinite number of points along the course of this yellow stick? What happens is it goes, this array of points goes forever and for always up that way, and forever and always down that way. And since there's an infinite number of them, poof, it's almost like magic. Now, this collection of points has a dimension. One dimension that we usually call length. You can call it whichever one you want, but we usually say length. So now this collection of points that I'm kind of helping you see with this yellow stick actually has a dimension. It has length. Okay. Let me remind you, we got length, but it's still the same width as 1 point. Remind me, what was the width of 1 point? Oh yeah, nothing. And it's still got the depth of 1 point. And yeah, that's nothing. So can we see this thing where the yellow stick is? Okay, the yellow stick's not there, but the line's still there. It goes along in here. It goes forever and for always up that way. It goes along down here. It goes forever and for always down that way. And you can't see it because it has no width and no depth. It does have length, though. It has one dimension. Okay, well, that's pretty interesting. What happens then if I take like a bunch of these, not yellow sticks, but lines? What if I line them all up? Okay, remember, it has length. This is representing a line. It's not a line, it's a yellow stick. Okay, so I have this line. It has length, no width, no depth. Okay, then I get a blue stick, which also has length, no width, no depth. I stick them together. I got 2 sticks. But if I'm talking about the lines themselves, I have 2 lines right next to each other. This one has no width, blue. Yellow has no width, blue. So 0 plus 0 would still be 0, wouldn't it? So when I put these 2 together, it still didn't have any width. And it never did have any depth. Okay, well, what if I get a third one? That's like 3 times as much. That's certainly going to be better. Yes, 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 no. Okay, because 3 nothings is still nothing. Okay, so now I'm going to do the same thing I just did. And I'm going to put like 1,000,000 between each one of these lines that we're thinking about using these sticks. So 1,000,000 between the yellow and the blue, and 1,000,000 between the blue and the red. All lined up nice and pretty in a nice little row. How deep is it? It's not deep. It's it's 1 point deep, and 1 point doesn't have any deep. It's 1 point wide, and 1 point doesn't have any wide. Well, actually, it's 3 point wide. It's 1,000,000 and something points wide. 3,000,000, 2,000,000 and 3 points wide. But 3,000,002 times 0 is, I'm sorry, still 0. Go figure. Okay. Now, again, what if I do it an infinite number of times? Okay, so I'll put an infinite number here, and I just have an infinite number of them lining up here. And eventually, I'm going to get this surface, which I'm going to represent with this piece of plastic. Okay? So eventually, I'm going to get this surface. How did I make this surface? Well, I made the surface by making a bunch of lines. Now, the lines didn't have any width, and they didn't have any depth. So, but look what happened when I did this. It has length because it was all lines, and it has width because I piled up an infinite number. And now remember, I've got this little piece of plastic with green around it, and the little plastic of green around it ends at the green. But the plane extends forever because it's composed of lines that extend forever and for always. All directions forever and for always. Okay, so remind that. So the piece of plastic with the green on it is just an assistance for our mind, okay? In our mind, we can see it. Now let's think about this. I can see a reflection there. You see that? Well, there's my living room window. Is the dog sitting there? Yeah, you can almost see the dog. He moved. Okay. When you take a two-dimensional object, length and width, and put it perpendicular to your line of sight, or maybe not even perpendicular, you can see it. The best thing we've got to an example of this to kind of help it get into our mind well is just what you see here, a reflection. This reflection has no depth. It has length and width. Okay, I know. We could argue with Professor Einstein about whether it has any depth, but we're not going to go there right now. Okay, so it has width and length, and it has no depth. Okay. Okay, but I can see it. Or like when you go to the movies and there's light projected on a wall there. You can see it, but it has length and width, but it has no depth. Same deal here. Okay, now what happens then, okay, if you turn it sideways? Okay, now you're going to have to imagine even more now, because this really has no depth, because remember, it was composed of lines that are only one point thick, and 1 point ain't thick. Doesn't have any thickness at all. It's 0. So if I line this up with my line of sight going right there to the camera, right like that, if it were really only one line or 1 point thick, notice that you couldn't see it at all, okay? Because it would have no thickness. It has length, width, no depth. Okay, let's play with that a little more here. Okay, here's my handy dandy point on my Rice-Al Band commemorative pen. I wonder how many lines I can draw through this point. Okay, now if a line is oriented differently, it's going to be a different line, okay, for the purposes of this argument. Okay, that is a line that goes through that point. Actually, it's a yellow stick on the top of the pen, but it's helping our imagination. Bear with me on this. Okay, so that could be a line. Look, I orient it that way, it's a line. That way, it's a line. How about down over that way? Yep, that's a different line. That's a different line. That's a different line. Oh my goodness, there's an infinite number of different lines, kind of like a dandelion going all out from this point on my Rice-Al Band pen. Pen, okay. Like all the way around, making this big dandelion flower like going around. There's an infinite number of lines that I can draw through this one point. Okay, that was Rice-Al Band. Okay, so what if I go back to Cougars winning the Southwest Conference, which doesn't exist anymore. Okay, now I could use this one and it goes through the Rice-Al Band pen. I could do this one, it does, but notice that there's only one way to put a yellow stick between the Rice-Al Band pen and the Houston Cougars Dr. Pepper. And I think in your imagination you can see that there's only one way to draw a line between the point here at the top and the point here at the top, okay? There's only one way to draw a line through 2 points. You say, you're right. Because I can put a whole bunch of lines over here. I can do this. I can do it every which way. Got myself another dandelion here. Another firework in the sky going. But no, but only one of them goes over here to my Rice-Al Band pen. There is one and there is only one. Okay, well, what if I get myself a third point? Getting high tech here. Okay, this is a vase that I bought my mama at the 5 and Dime. Okay, you don't even know what 5 and Dime is. It's kind of like Walmart, only not as nice. Well, actually, the one I went to was nice. It's a thing that has inexpensive items that you can buy. And I bought this, and it was a lot for me, and I bought it for her for Christmas, and she kept it, and when she died, I got it, and so now I have it. Okay, so I'm going to use this point at the top of my mama's vase, and I'm going to use my Rice-Al Band pen, and I'm going to use my Cougars win the Southwest Conference. But first off, I'm going to just play around with the plane and the Rice-Al band, pin, and the Cougars. Okay, so first off, if I take a plane, remember I could only draw one line, right? Only one line. But look what happens. If I put a plane right here, that touches both of them. See? It touches the top of the pin, the one point. In other words, this plane contains this point and this point. Okay? That's the right way to say it. Oh, but look, when it's oriented differently, it's a different plane. And now this plane also contains the 2 points. This plane contains the 2 points. This one, this one, this one, this one, this one. There are an infinite number of planes that contain these 2 points. Do you see how that works? Here's a plane, here's a plane, here's a plane. Every time it's a different orientation, it's a different plane. Okay? Now I get my mama's face. There's my mama's face. And so now I have a third point. I'm going to have the top of the pin, the top of the bottle, and the top of the vase. So here I'm twirling around. Oh, look. When I put it there, I can't twirl it anymore. If I just have these two, I have an infinite number of planes. If I just have the pin and the bottle, I just showed you there's an infinite number of planes. If I only have the pin and the vase, there's an infinite number of planes. But as soon as I introduce that third point, there is only one plane that can go through all three of them. So there is a plane that goes through all three of them, and there's only one plane that goes through all three of them. Okay. This is geometry. Some definitions of those things that aren't defined. How interesting, huh? Okay, so the things that aren't defined here, but we've got to kind of think about them so we know what we're talking about, or try to anyway. A point we say has no dimensions, no length, no width, no depth. It's often referred to as a location in space. It's really hard to narrow it down, but it's something that's in your mind, and you can figure it out in your mind. It's not a big deal. Okay, a line is a collection of points, an infinite number in a line, straight, so that after an infinite number is piled up in a nice straight line, 1 point thick and 1 point long, there's one dimension. A plane has two dimensions. It's kind of like a surface, like maybe a reflection in a mirror, or like on a movie screen at the movies where it's created by light. A plane has two dimensions. Okay. Let's look at a couple of other terms. Now I am actually defining these terms. The term collinear refers to points that are on the same line. So this would be two or more points that are on the same line are called collinear. Yeah, it's got two L's. I don't know why, but it does. And coplanar is lines or points or shapes or anything else that are in the same plane, that are contained in the same plane. We would then call them coplanar. We're going to talk about some postulates. So first I have to tell you what a postulate is. Okay. A postulate, and the synonym for that is axiom. Both of these are perfectly good words to mean this. They refer to the same thing. It's just some mathematicians like the word postulate and some like the word axiom. A postulate or an axiom is a concept that we will accept without proof. We'll accept without proof. That does not mean it can't be proven, but it does mean we'll accept it without having to prove it. On the other hand, there's a theorem. A theorem must be proven, and we'll prove a lot of them. An abbreviation for theorem that's commonly used is THM, and you're perfectly at liberty to use that abbreviation. Let me point something out here. This is not theory. You may not say theory. It's not the same thing. It's not a theory. It is a theorem. Okay, two postulates, our first ones, will be here, which were just illustrated in the video, and that is through any 2 points, there is uniquely one line. That's commonly referred to as 2 points determine a line. We just saw that with the Coke bottle and the Rice Alban pen. Oh, there's a Dr. Pepper bottle. 2 points determine a line. As soon as you have 2 points somewhere in space, there is one line, and there is only one line that can be drawn through that. In this case, in this circumstance, uniquely is one of those words that is a math term that has a specialized meaning. When we say there's uniquely one, we mean there is a line, and we mean there is only one line. So any 2 points you got, you can draw a line through them, and you can only draw a line through it. Now, if you draw a red line and then you draw a blue line, you hadn't drawn 2 lines. You drew the same line in multicolor. Okay? All right. And then the next postulate here, or axiom, whichever one you want to call it. Through any 3 non-collinear points, there is uniquely one plane. Again, uniquely means there is one plane that can be constructed, and there is only one. Or the way it's usually said is 3 points determine a plane. I was actually just talking a little while back with a friend who gave a lecture, and he gave a lecture on 3 items that worked together, and he called it a 3-legged stool. And he wanted to call it, he called it a 3-legged stool because it's always stable. And he thought about it and he said, well, I guess it's always stable because they form a triangle on the surface. Figure that one out. That's not correct. Unfortunately, or fortunately for him, I was there at the lecture, and I knew that it was really 3 points determine a plane, because wherever you put 3 points, so if I have my 3 pins here, all 3 will always touch the plane. Okay? No matter how there's Ollie. No matter how I configure it, if there are 3 of them, it will always touch the plane, and it will always be stable. Grab some pins and play with it and see that that happens. Okay. How do we name points and lines? Okay, naming points and lines. Well, points. First off, this is not a line. It's some blue ink on a piece of paper. It helps our minds imagine a line, but it's not a line. It's a representation drawn on paper with blue ink. It has 3 dimensions, length, width, and height. Okay, it has a little bit of width, quite a bit of length, and you're saying, yes, I don't think that has any height. Yes, it does. There is some blue ink that the printer over there squirted on it. It isn't much height, but it's some height. It is 3 dimensions. Well, these dots are not points, but they represent points. And so we'll use those to help our imagination. And I've labeled them with capital letters. Generally speaking, in geometry, we use capital letters. In algebra, generally speaking, you use lowercase letters. Now, yet you can switch them around, but we just usually don't do that. In geometry, we're going to usually refer to capital letters as representing geometric figures, in this case, points. Okay, how do you name a line? By choosing any of the 2 points on the line. Doesn't matter what the order is. Okay, here's my line here, my blue ink, and I could say that this is the line BE because B and E are on there. So I can name it BE to designate that it is a line. Again, a line, remember, goes forever and for always that way, forever and for always that way. And so I will draw a double arrow on top like that to designate that it's a complete line that keeps on going forever and for always. I may choose any 2 points. I may choose them in any order I want. I can put another point there and name it and call it, you know, H for Hamilton, and I can stick an H there and do it. Okay, I can choose FD, that'll work. Any 2 points on the line with a double arrow on top drawn like that. Doesn't matter which 2 you choose. Now, a line segment is a little bit more particular. You will recall that a line segment is a portion of a line. The line is the one that goes forever and for always in both directions. A line segment is between two endpoints. So for example, right there from C to F. Okay. I'll cover up the other. So now what I'm looking at is the portion of the line. The line's the whole thing, but I'm looking at the portion from C to F. C is where it ends. F is where it also ends on the other side. So it's called the end points. Aren't mathematicians just really creative in naming things? But anyway, it's helpful. They're the end points because they're the points at the end. You must use the end points to name a segment. So I have to use C and F. C and F. I draw a line over it with no arrows, indicating that it does not continue. I can also call it FC, it doesn't matter. But I can't name it by any of the points in the middle. I have to use the endpoints. For example, if I wanted to name it CE, then that would not be this point. This portion. It would only be between these two. Okay? So, that's naming a line segment. A ray, I'll just start with this ray right here. A ray begins at a point and continues on the line. It's kind of like half of a line, except you can't really say half of a line because a line is infinite and half of infinite is still infinite, and so you get your mind all wrapped around real funny when you try to think about that. So basically, yeah, it's half a line. It's from D going on, but it's still infinite. It goes on infinitely, in this case, in that direction. The way to name a ray is you must name a ray based on the end point first. Okay, so I'm going to put D because that's the end point of the ray that begins here and continues through E and F. And then I can choose any other point on it. I can name myself another one if I want to, just to show the direction I'm going. So I start at D and I continue through E. That's the ray D, E. So it's only got one arrow in it, and the arrow's going to the right. This could also be the arrow, the ray DF, and I could name it any other point along in here and use that. Notice that it's two things are not okay about rays. It's not okay to do this and put the arrow backwards. Nope, can't do that. And it's not okay to draw a cutesy little half arrow like that on it. Now, this cutesy little half arrow is a mathematical term, and you may have seen it and thought it just meant the same thing, but it doesn't. We'll learn that second semester. So your arrow's got to have both of the little parts of the point on it. So you can't use it that way. Okay, so that is the ray D, which continues through E and F and goes in that direction forever and for always. Over here is the other ray that starts at D, but it goes the other direction forever and for always. So this one would begin at D. Again, D would have to be the first letter, and then I can choose any of the others. And the arrow always has 2 points, and it always has 2 prongs on the point, and it always goes to the right, can't go to the left. We call these opposite rays. Opposite rays are collinear. They come from the same line. It's like half of a line and half of a line. If you put it together, it makes the whole line. Now, as I just mentioned, there's no such thing as half of a line, but we'll go with that. It has to be from the same line, it has to be collinear, and it has to have the same end point. So just being from the same line is not good enough. For example, if it's from the same line here, and in one direction, say it starts at C and goes like that, okay? That would be a ray. And then if you had another one that started at D and goes the opposite direction, okay, that's not opposite rays. It's 2 rays. They are collinear, but they do not have the same endpoint. There's this overlap. It's got to be exactly the one line. Okay? And another thing that doesn't work is to have, okay, so I'm telling you here that collinear is not enough. It must have the same endpoint. And then here we see that the same endpoint is not enough. They have to be collinear. Here we have two rays, AB, AC, that have the same endpoint. They share an endpoint, but they are not collinear because they aren't in a straight line. Okay, so now we're going to try a little exercise here. You need to have already gotten three flat things that are kind of like planes. Here's the flat things that are kind of like planes that I got. And at the moment, I've got my We3 book that my mama got me. This was my first grade reader. I really liked it. It's about Dick and Jane and Spot. And I really liked it, so she bought it for me, and I still have it. Okay, so there's We3, but it's flat. You need to have three things that are flat and kind of rectangular. Here's a piece of cardboard. I don't know, piece of cardboard. And I have this handy-dandy little plate that is for cheese, I think. Okay? So we're going to do some exercises for this. For example, what happens when you put two planes together? Okay? So here, I'm putting two planes together. Notice that the intersection of the plane is a line. There are a series of points where these two planes intersect, and it's this line right here. The planes go on forever and for always in all directions, and the line does also. The intersection of the two planes is the line. Now, there's lots of points on this line, so it is true that a point, say right there, is part of the intersection, but it's just part of it. The whole line is the whole intersection. So what we're going to do now is we're going to put our three planes together and try to do different things with them, okay? And so I have several exercises here for you to attempt. You're going to do them one at a time. Please pause it and get it. Don't just wait until I show you the answer. Okay, here's the first one. Three planes intersect in one line. Pause it and figure it out. Okay, here's three planes intersecting in one line. I don't think I'm going to do this with the cardboard. Okay, there's two planes intersecting at one line, and there's the third one. All three intersect at the same line, which is right down here at the corner. Right down there where the marker is the line where they intersect. Okay? And again, the line continues both directions, and the planes continue in all directions. So this is three planes intersecting in one line. Okay? The next one, three planes intersecting in one plane. Three planes intersecting. You can't do this. Let's look what happens. If you remember, 3 points determine a plane. So if they're intersecting in one plane, that one plane would have 3 points that are on all of them. That would mean that they are all the same plane. That you've named it differently doesn't make it a different plane. Here with my three pieces of cardboard, it looks like I can stack them. But remember, they have no thickness. They would all be together, and they would be one plane that has three names, and renaming it doesn't make it different. A rose by any other name would smell the same. So that one doesn't work. Okay. None of the planes intersect. Pause it and do that one. Okay, none of the planes intersect. Here are my planes. If I do them out parallel, like this, they don't intersect. They would all three have to be parallel, because remember, the planes go forever and for always. So you can't just say these don't intersect because they don't touch. Okay? You can't say these don't intersect because they don't touch, because this is just pieces of cardboard that's telling us about planes, and the planes go on forever and for always. So this plane will extend into there and it will intersect. So anytime they're not parallel, they will intersect. Three planes that don't intersect have to be parallel. The next one. Two planes do not intersect. The third plane intersects the other two. Okay, pause it and try that one. Okay, two planes that do not intersect, and a third plane that does. These two do not intersect, they are parallel. The one on the table intersects both of them. Two planes that do not intersect, and a third plane that intersects the other two. Okay, the last one, exactly two planes intersect, the third plane does not intersect the other two. Okay, give it a try. Okay, here are two planes that intersect, and a third one has to not intersect this. Okay, if I put it parallel to the, remember they got to be parallel to not intersect. If I put it parallel to the left one, it intersects the right one. If I put it parallel to the right one, it intersects the left one. And again, you're not allowed to say it's up here because these continue. And so they will intersect it even though the cardboard is not touching it. The cardboard isn't the plane. It's just something to help your imagination. Okay? And here endeth the lesson.